So this unit deals with two main areas. It deals with what are called rational functions, and we're going to be spending 2 days on that, and then function operations, and we will be spending, I think, 4 days on that. This is chapter 9 and chapter 10. So we're beginning today by looking at rational functions and transformations of rational functions. This is a very basic lesson. There's not much to it. It's going to be testing your algebra skills more than anything. And we should have time today to take a look at your exams from Friday. So what are we looking at today? We're looking at two new graphs. And these aren't, well, one of them is new. The other one is not really new. This function here, y equals 1 over x, you learned about last year in Math 20-1. You called it a reciprocal function. You started off by looking at the function y equals x, and last year you learned what 1 over functions look like, and it has to do with asymptotes and increasing and decreasing values of y. So you've seen this before. This shouldn't be a surprise when I show you what it looks like. This function is new. Well, I guess you might have encountered it last year because your teacher might have said, look, if we can take any function and find the reciprocal of it, and you know what y equals x squared looks like, you ought to be able to figure out what 1 over x squared looks like. But we're not worried here about how we arrive at the pictures of these two functions. We're just worried about the algebra involved when we transform them into functions using a, h, and k. And we'll get to that. There's something about rational functions that produces non-permissible values, and I think you can see why you get non-permissible values for a rational function. It's because there's a denominator, and the denominator contains x. So potentially there are values of x that cannot be equal to 0. For example, in this function 1 over x, x cannot be equal to 0. In this function 1 over x squared, x cannot be equal to 0. So that leads to non-permissible values. And what we're talking about in the second thing is not just what the non-permissible values are, but what's the behavior of the graph close to those non-permissible values. And when I say behavior of the graph, what I mean is the behavior of the function, and what I mean there is y. So that second statement is saying it's important for us to know what y is doing when we get close to values of x that we are not allowed to use. And we're going to continue to do that tomorrow. Today it's kind of we're just dipping our toe in that water, and tomorrow we'll expand on it a bit more. So what a rational function is a function of the form f of x equals, okay, this is how a textbook would define a rational function. And there's a bit of a problem with it, and I'll talk about that problem. The textbook definition of a rational function is any function of the form f of x equals n of x over d of x. N I'm using as numerator and d I'm using as denominator. And what it's saying is a rational function is any function where n of x and d of x are polynomials. So a polynomial over a polynomial gives you a rational function. For example, y is equal to x minus 2 over x plus 3 is a rational function because the numerator is a polynomial, the denominator is a polynomial. Y is equal to 3 over x squared plus 1 is a rational function because 3 is a polynomial. It's a boring polynomial, it's just a constant polynomial function, but it is a polynomial, and x squared plus 1 is a polynomial. However, and this is where I think this definition that you're typically given it has an exception to it. This is not a rational function. It's not. It's a linear function because I can write that as y is equal to 1/2 x plus 4. So there's no denominator. And, now we get into the nitty-gritty. In my mind, the better definition of a rational function is any function that has a denominator containing a variable. I think this is wrong. I think n of x over d of x saying d of x can be any polynomial is wrong. because d of x cannot be a constant polynomial. There must be an x in the denominator. So that's the definition of a polynomial function. So generally speaking, you can identify a rational function. So that's the definition of a rational function. Generally speaking, what I'm telling you is a rational function is a function that has x in the denominator. That's the bottom line. So as a warm-up, we're going to look at what I call two basic rational functions. They're the graphs of f of x equals 1 over x and f of x equals 1 over x squared. So we'll start with the 1 over x and just talk briefly about it. We have to describe all of the properties, which we'll get to in a second. But I would like you to focus your attention on the fact that there are these, well, I'll call them key points. Just like if you had y equals x squared, you know the origin is a key point, and you know 1, 1 and negative 1, 1 are key points, and 2, 4 is a key point. Key points are points that we can use in order to find out what the graph of a transformation of that function would look like. And the reason why these are both key points, you don't need to do this, you don't need to write this, but you know, if you want to, you can. If y is equal to 1 over x, then when I take x at negative 1 and I take 1 divided by negative 1, I get negative 1. When I take x at 1 and I go 1 divided by 1, I get 1. And what happens as we go further away from the origin on the x-axis, if you go to say negative 2 or positive 2, you get a smaller value of x. Because the function is 1 over x, as x gets larger, 1 over x gets smaller. So that's why when x is 2, y is a half. Or when x is negative 2, y is negative 1/2. The opposite is true as well. If I go to x equals 1/2, which is right here, 1 over x simply means take the reciprocal. So that's one way of looking at it. And if I take 1/2 as an x-coordinate, I take the reciprocal, all of a sudden now the opposite is happening. I get closer to 0 and y gets bigger instead of getting smaller. So that's why 1/2, 2 is a key point as well. So these are just some key points that we can use in order to understand what's going on. And I say it that way because a very important thing is going on. As x gets bigger and bigger and bigger, y gets smaller and smaller and smaller to the right. But there's no limit to how small, this is a weird thing, there's no limit moving to the right to how small y can get. It will always be getting smaller and smaller and smaller, but there is kind of a limit of 0. It can't reach 0. And that's why, and after I printed this, I thought, well, you could have done a better job with the graphics. That's why I have an asymptote here. It's faint on your handout, but I think you can still see it, yes? So there's an asymptote there. Similarly, if I go really, really close to 0 for x, (1 over 10,000) at x equals 1 over 10,000, that's very, very close to 0, but the reciprocal of that is 10,000. So what happens is the function is taking off in an asymptotic fashion against the y-axis, and that's why we have a vertical asymptote as well. So what are the features of this graph? How can we describe the properties of this graph? I'm going to get rid of this table of values. I don't think you really need it. If you've written it down, you get the point. Well, there's a vertical asymptote. At x equals 0. There is a horizontal asymptote at y equals 0, we can say what the domain and range is. The domain is x is not equal to 0, and the range is y is not equal to 0. And beyond that, there's nothing to be gained by writing anything else. That's the main idea. That's the thing that I want to get across to you. Any questions with that first graph? Okay. By the way, there's no x-intercepts, there's no y-intercepts. That should be obvious because those are asymptotes. Let's take a look at the second graph. The second graph is a little bit different. When you go back and you look at the first graph, these two things, there's a word for this shape, by the way. It's called a hyperbola. You don't need to know that, but just in case you're wondering, it's called a hyperbola. These two branches of the hyperbola are symmetric with respect to x and y. You know, it curves just as much horizontally as it does vertically. In other words, if I were to take this shape here and reflect it horizontally, I could rotate it and it would still match. Okay? Well, reflect it horizontally and vertically and then rotate it, it would still match. This one is different though. It's taller than it is wide. And the reason for that can be illustrated, I think, if you were to take a point for x like 1/10, which is very close to being x equals 0. It's very close to the y-axis. And if this were y equals 1 over x, this would be 10. But it's 1 over x squared, which makes it 100. So it climbs more rapidly towards infinity when we're against the y-axis than the other function does. Similarly, if you go to larger values of x, let's just go to 2. If this were 1 over x, the y-coordinate would only be a half. But since it's 1 over x squared, it's 1/4. It's 1 over 2 squared, which is 1 over 4, which is 1/4. So it climbs more rapidly and it descends more rapidly, and that gives it that elongated shape. The other important thing to recognize here is that everything is positive. This graph lies entirely above the x-axis because of the squared nature of the function. It's going to take any negative x and it's going to make it positive before you reciprocate it. So what can we say about this function? Well, we can say the same kinds of things that we said about the previous function, which is that there's a horizontal asymptote and there's a vertical asymptote. The vertical asymptote is at x equals 0. The horizontal asymptote is at y equals 0. We can say that the domain as x is not allowed to be 0, but we cannot say the range is y is not allowed to be 0. There's a bigger picture here, and not only can y not be 0, it cannot be negative, which means y must be greater than 0. Now, I do want to add a couple more things, because I started off today's lesson by saying it's important that we understand what is happening to the function as we approach a non-permissible value of x. And I'll go back to this one now. The non-permissible value of x is 0. So this is how we write it. As x approaches the non-permissible value of 0, y approaches positive or negative infinity. This will be very important for tomorrow. As you get closer and closer and closer to x being 0, y either approaches infinity or negative infinity, depending on which side you're on. Okay, it doesn't matter. If you take calculus with me, I'm going to write down what we would write in calculus in green, and you do not need to write this down. In calculus, we would say, as x approaches 0 from the left, y approaches negative infinity. That little negative on the 0 means from the left-hand side of 0. And I'm just pointing this out so that when you're in my calculus class next semester and you see this, it won't be a total surprise. You will have seen it before. We could also say as x approaches 0 from the right, y approaches positive infinity. We can make a distinction between the left and the right-hand side. We want to talk about what's going on with this function. Well, this function is pretty unambiguous. As x approaches the non-permissible value, y approaches infinity. It doesn't matter which side you're approaching from, the left or the right, the function goes up. So all this first little kind of warm-up is about is you recognizing what this graph looks like, y equals 1 over x, and what this graph looks like, y equals 1 over x squared. Does anybody have any questions about those graphs? All right, so if we apply the parameters a, h, and k to the function f of x equals 1 over x, or to the function f of x equals 1 over x squared, we get a transformed function. Notice we don't worry about b here. B is too much. There's another reason why we don't want to include b, but b is just making things too confusing at this point. So if I apply a f of x minus h plus k to 1 over x, I'm going to have a times 1 over x minus h and then plus k. And the result is I get these two equations. The first function, 1 over x, becomes a over x minus h, then plus k. The second function becomes a over x minus h squared plus k. That's all. And I think I've said to you a number of times, I really ought not to have to tell you this. You should be able to take any function in the universe and apply this template to it. And in this case, it's actually even easier because there's no b. All right, so let's take a look at some examples. First of all, that's all I'm saying. 1 over x becomes a over x minus h plus k. 1 over x squared becomes a over x minus h squared plus k. To be totally transparent with you, I have never seen any diploma exam question dealing with what's below the line. Okay? It's unimportant. Well, I mean, anything can be important if you see it, but it's kind of something that's treated very lightly. We're going to be focusing mainly on what's above the line, these types of functions. So, two functions are given. We're going to see a lot in this unit that when you're given functions, sometimes you're given one of the functions as an equation and the other function as a graph, or you might be given one of the functions as an equation and the other function as a table of values. It's not always two graphs or two equations. So there are the two functions, and what we are asked to do is find the equations of each of the two functions in the form y equals a over x minus h plus k. So I'm telling you that both of these functions are transformations of 1 over x. If I'm saying we want to write these, if I'm saying that we want to write these in this form, then starting with f of x, and I've just put the graph here so that I can refer to it. Okay, you've got it right on paper there. Then f of x must be a transformation of 1 over x. So we need to identify three parameters. We need to identify the parameter a, the parameter h, and the parameter k. But 1 over x, we know has asymptotes centered at the origin, right? So why on earth would the asymptote of the function that we're after, so I'm going to write in brown y equals 1 over x. And I'm just going to trace this out in red. This is the function whose equation we're after. And I'm going to put its asymptotes in red. So why on earth would the asymptotes have moved? Why would the horizontal asymptote no longer be at y equals 0, but at y equals 2? The answer is the whole thing has been shifted up at 2 somehow. Not somehow, it's been shifted up by 2, which means k must be 2. This is kind of like what I was talking about with logarithmic and exponential functions and their asymptotes, except this function has 2 asymptotes. Why is it that the vertical asymptote of the function we're after, let me write this out so you can see it. Why is it the vertical asymptote of the function we're after is not at x equals 0? Well, because it's been shifted, the original function has been shifted 1 to the left, which means that h is -1, and I guess in keeping with my color coding, this is all about the red function, right? So how are we going to find a? Everybody should know the answer to this question. It's got nothing to do with rational functions. It's a missing parameter. We're going to put in the parameters we know and then pick an ordered pair and put the ordered pair in to solve for the parameter, a. So what is the equation of this function? It's y equals a over x minus negative h, which would be x plus 1, plus 2. And I've covered up a number of key points here, but you're told this is a point, you're told this is a point, you're told this is a point. You have a number of points you can use. And by the way, I'm glad to kind of observe that none of you were writing all of this on your graph, I don't think. I think when you do, it starts to clutter things up. So when you look at your graph in its unadulterated form, we have 0, 4, we have -5, 1, and we have -2, -2. Did I read those correct? Looking at your graph? Okay. It really shouldn't matter which one we use. And I'm not going to do so, but we could find the missing parameter a using the first point and then find it again using the second and find it again using the third. You're going to get the same result, which is kind of weird, but I would recommend using 0, 4. I think, well, I'm going to use 0, 4. And now I explain to you why the added benefit of that is 0 plus 1 is just 1, so it turns out we don't even have a fraction. Is there a question? It's 0, 6? Thank you. Thank you. It's 0, 6. So we're going to end up with 6 equals a plus 2, which means a is equal to 4, and now we've got the answer to the first part of the question. It's 4 over x plus 1 plus 2. And if you wanted to, you could go ahead and put in, you know, those different numbers. -5, if you put it in for x, you would end up with -4 on the bottom here. 4 over -4 is -1, plus 2 is 1. That's what we're supposed to get. You could confirm that it's going to work for the other points. So any questions with finding f of x from this graph? Okay. Another skill that you need to be able to do is to find a function like g of x using a, h, and k when it's been simplified. And if I were to take, for example, I go back to this function. I could put these together with a common denominator. The common denominator would have to be x plus 1 which would mean I would have to multiply the top and the bottom of this 2 over 1 by x plus 1. Just take a minute here, a second, and picture what I've done here. All I've done is I've found a common denominator, which is a very simple common denominator. And what I would get for the function is y equals, it's going to be something on x plus 1, and it will be 4 plus this thing, which is 2x plus 2, which gives us y equals 2x plus 6 over x plus 1. And in fact, you might see an exam question where instead of being asked to find a, h, and k, you're asked to write the function in that form for f of x. Are you with me on that? So functions that look like linear over linear are typically functions you can write in this form, a over x minus h plus k. And what we have to do for g of x is unwind that somehow. We have to figure out what that would look like if it were in that other form. It's kind of like going from completed square form or vertex form of a parabola to the standard form, or back and forth. And there are different ways to do this, and I've found that the best way at this point for us to do this is to divide 4x plus 10 by x plus 3 with synthetic division. This is the squared one. This is the reciprocal of x squared, and it's just, as I said, it's treated very lightly. We're given these two functions. I think you can see that since the bottom of this is quadratic, this is a variation of 1 over x squared, which means each of these can be written as a over x minus h quantity squared plus k. By the way, I'm just going to pause here. Not all rational functions can be written as variations of 1 over x or 1 over x squared. Okay? We'll look tomorrow at more variety. So how do we write this h of x in that form? All we do is we take that 6 and put it over here, take the negative that's in front of this fraction and put it on the top, and we're done. And maybe I think everybody, the bigger point is you should know that this function h of x is 1 over x squared reflected vertically and then translated 4 to the left and 6 up. We're not going to worry about drawing it. That's just, there's nothing to be gained by that. K of x, we can recognize that this denominator happens to factor into x minus 5, which is x minus 5 squared. And that means that k of x, if you start with y equals 1 over x squared, that means that k of x is 1 over x squared stretched vertically by a factor of 3 and then shifted 5 units to the right. In other words, a is 3 and h is 5. Any questions with example 2? All right. Final example, a rational function of the form y equals a over x minus h, then plus k, has an asymptote at x equals negative 6 and passes through the point 2, 1. And then you're told the x-intercept and you're asked for the y-intercept. So I hope that one of the things you've learned in this course is that if you look at a question like this and you were asked for something like the y-intercept of a function, you need to know the function. You know, forget about all the information given. If I say, what is the y-intercept of a function, then you need to know the equation of the function. And that means your goal, your primary goal right now, is to determine these three parameters. If we know these three parameters, we've got the equation of the function. We could find anything we want about it. So we do know one of these parameters. It's that h is -6. You're not told that that's a vertical asymptote, but once again, everybody, if this is where you would find the asymptotes of 1 over x, and we have an asymptote over here at x equals -6, this asymptote must have been shifted to -6, which means h is -6. That means in the function you're going to have over x plus 6, right? But h is -6. So that's a start. At least now we know what the value of h is. I don't need this. So how are we going to determine the values of a and k? Well, we can start populating a table of values. Passes through 2, 1. But here's the issue. Here's an issue. That's only one point, and we have two parameters. And we've seen questions like this before. I hope you remember we've seen them. That if you have two missing parameters, you need 2 points. What's the other point? Joanna? Well, I've got 2, 1 here. 1, good, 1, 0. Because the x-intercept is at 1, x-intercept's where y is 0. So we now can set up a system of equations by putting in 2 for x and 1 for y. Let's do that first. Well, first of all, I should say, let's put in the -6. So now we have an equation that we can populate with an x and a y, right? We need to have that known parameter in there. So what will my first equation be? My first equation is going to have 1 equals a over 2 plus 6 plus k. So, you want to be careful here. I at least have to be very careful that you put in the numbers where they belong, that the 2 goes in for x and the 1 goes in for y. Our second equation is going to be 0 equals a over 1 plus 6 plus k. And again, the x-coordinate, the y-coordinate goes in for y, and the x-coordinate goes in for x. Are you with me on that? Okay. So now what you need to do is simplify these two. I'm going to do this in 2 stages. I think you could probably skip a step, but equation 1 can be written as 1 equals a over 8 plus k. Equation 2 can be written as 0 equals a over 7 plus k. All I've done is I've added the 2 and the 6 to get 8, and the 1 and the 6 to get 7. And then, when I've tried to teach you in this course, and if I had you in 20, I've really tried to teach you this, forget about rational equations or anything. Fractions are things that you would rather not work with. So if you have fractions, do what you can to get rid of them. And in this particular case, what I can do is multiply both sides of this top equation by 8, and both sides of the bottom equation by 7. So what does equation 1 become? Well, it becomes 8. 8 is equal to a plus 8 k. So 8 times 1 is 8. 8 times a over 8 is just a, and then 8 times k is k. The second equation, equation 2, 7 times 0 is 0. 7 times a over 7 is a. And then 7k. And subtract the equations now. I don't know if you remember this about me. I don't particularly care for subtracting equations. I would rather multiply the bottom equation by -1. I think this is such a simple case that subtraction is pretty straightforward. We go 8 minus 0 is 8, so I'm subtracting this equation. 8 minus 0 is 8. A minus a is nothing, and then we're left with k equals 8. So we've determined k. We can add that now to our list. And now we're left with finding a. See, at this point in time, though, it's got nothing to do with rational functions. You're solving a system of equations. Once you find one of the unknowns in your system of equations, you just go ahead and load that value back into any of the other equations that has the two parameters. So if I use 0 equals a plus 7k, and I put in my k of 8, I'll have a plus 56 equals 0, so a is negative 56. And if you would have put that k equals 8 back into the top equation, you still would have got negative 56. You can try it on your own. You'll get it. Okay? So now we know a is negative 56, and now we know the equation of the function. The equation of the function is y is equal to negative 56 over x minus h plus k. So let's check something out before we answer the question. If I take this function, I'm going to load it into my calculator for y. I'm not really interested in the graph, by the way. I put in negative 56 over, in brackets, x plus 6, and then plus 8. And I'm going to set my table up to allow me to enter values of x. Okay? If I go into my table now and I enter x equals 2, I get 1. 2 comma 1 is a point. If I enter x equals 1, I get 0. It's a point. So that checks out. Now, how am I going to find the y-intercept? I'm going to put 0 in for x. If you want to do that on paper, your y-intercept will be negative 56 over 0 plus 6 plus 8. Can you do me a favor and run that through your calculator? I think it's, I don't know if my brain's thinking right here, negative 1.3 repeating. So it's negative 4/3. But, you know, at this point in the game, you could just put in 0 for x and see what you get. So it's negative 4 over 3. Okay. That's it. That's the lesson. You know, I could have asked you to determine the values of these two parameters in the function, which would simply mean you would convert the 8 over 1 to something over x plus 6 and put them together and see what you get.